Hello everyone and welcome back to lecture 8. In this part of the lecture we will talk about preliminary design of some of the reboilers. So the design of reboilers consider the heat transfer characteristics of boiling that you have discussed with Vani in lecture 4. And when we are looking at design of these reboilers, we normally want to operate below a critical heat flux. The reason being because if you're operating above this heat flux, you have the potential of melting the system or burnout. So that is why we always try to operate below critical heat flux. And here is the rationale for that, because if you are above critical heat flux, you either have low heat flux or you can increase the temperature due to the generation of bubbles at the surface of the metal. So at the safety limit, we have a heat flux of less than 70% of the critical heat flux. It means that we have a safety limit of around 30%. And just to remind you what is critical heat flux in case if you forget. So critical heat flux describes the thermal limit of a phenomenon where a phase change occurs during heating, such as bubbles forming on a metal surface that you are using for heating water, and which suddenly decreases the efficiency of heat transfer, thus causing a localized overheating of the surface. Okay, and that can cause either a burnout or surface melting. Now, the preliminary design of kettle and horizontal thermosiphon reboilers can be based on the phenomena of pool boiling, okay, and it's more commonly known as in nucleate boiling regimes. Okay, so here, if you remember, you have discussed this graph with Veni in detail, where you have on y-axis you are looking at the heat flux of the system, and on x-axis you have the excess temperature. That is the difference between the surface temperature and the saturation temperature. And you remember you had this kind of curve where you had an increase in heat flux from region 1 that is due to natural convection. Then you have region 2 of pool boiling where you have nucleate boiling and where you achieve the maximum critical flux. And we are, as I said, we are operating at around 70% of this value here. So we are mostly designing in this region. And if you look at the temperature difference is quite low, but we have significant high heat flux. And when we are talking about pool boiling, just to remind you again that in pool boiling, the heat surface is normally surrounded by a large body of fluid in which the fluid motion is only introduced by natural convections and motion of the bubbles. Okay, so you don't have forced convection there. Now, boiling is a very complex phenomenon, and that can be presented by a number of correlations. And for example, here we have a correlation that is presented by Palin, and this is just shown as an example. But you can use a number of equations and number of correlations to predict, for example, boiling in different regimes. So for exam purposes, you don't have to memorize these equations because you might get a different equation depending on a different scenario. So if this question comes to exam, you will be given the equation and the required parameters for you to solve the equation. Okay. So here, one of the simplest correlations that we use for nucleate boiling for a single tube was proposed by Palin. And Palin equation gives us an empirical correlation between heat transfer coefficient to the boiling heat flux and the properties of the boiling liquid and the surface that is being heated. Okay, so here you have the nucleate boiling heat transfer coefficient, the pressure of the liquid, and the critical pressure. And the critical pressure in Palin's equation for nucleate boiling refers to the vapor pressure of the liquid at the boiling point. Okay, and above this pressure, the nucleate boiling cannot occur. And if you are operating at pressures above critical pressures, the liquid will directly transition to vapor phase without actually boiling. And here QS is the nucleate boiling heat flux that, for example, we can calculate from these kind of graphs where the heat flux is given as a function of temperature for a specific liquid. Like here, this graph is for water, but we can have similar graphs for different liquids. And this QS, if we talk about QS in terms of rate of heat transfer, we can also write it as a function of heat transfer coefficient times the temperature difference between the wall and the heating surface. Okay, so if we know the value of H and B, we can calculate QS, and if we can find out the value of QS, we can calculate H and B for the system. Now, this correlation or similar correlations can be used for the preliminary design of kettle and horizontal thermosiphon reboilers for vaporization of single component. Okay, but we can actually use this equation for close boiling mixtures without too much error. If we have similarly boiling components, then we can still use this equation. Now, boiling heat transfer coefficients for tube bundles can also be achieved, for example, by modifying this equation. And we can use that to design the kettle and horizontal thermosiphon reboilers. But that is actually the outside the focus of this course. So here we are just looking at for a single tube here. But a similar equation that we can use for example, for tube bundles is what was introduced by Motinsky. Okay, and as you know that when we are talking about design of a kettle reboiler or a horizontal thermosiphon reboiler, we want to calculate what is the critical heat flux of the tubes. Okay, because once we know what is the critical heat flux, we can calculate what is the for example, our operating heat flux in terms of the QS, that is the nucleate boiling heat flux, because we operate around, as I said, up to 70% of critical heat flux. So once you decided that you want to operate, let's say 50% of critical heat flux or 40% of critical heat flux, and you know the value of critical heat flux, you can calculate what is your actual operating heat flux of the boiler. So here we can use Motinsky's equation to calculate or estimate what is the critical heat flux for a single tube. And here QC1 is the critical heat flux of the single tube. And again, it depends on the operating pressure of the system and the critical pressure, just like what we explained in the previous equation. And here, this equation gives you critical heat flux for one tube, but you might be designing kettle boiler where you are using a tube bundle, and it means that you have to correct the critical heat flux for the whole tube bundle. And we can do that by introducing a correction factor in this equation here, and that correction factor is given by phi b, and we can calculate this phi b by this formulation here, and that is actually a function of the diameter of the tube bundle. Okay, so not only one tube now, but the diameter of the whole tube bundle, the length of the tube, and the area of heat transfer. So once you know the value of critical heat flux, you can, again, as I said before, that you can decide that what safety factor you want to operate at. Let's say you want to operate at 70% of critical heat flux, and that gives you the value of QS, and then based on that you can calculate H and B. So most of the correlations for the design of reboilers, they use iteration. So for example here, if we want to know the value of H and B, then we need to add the value of QS. So if you don't know the value of QS, then you have to solve this equation and this equation simultaneously in a way that both equations give you same value of H and B and QS. Okay, that is the case for design of kettle and horizontal thermosiphon reboilers. For the case of vertical thermosiphon reboilers, it is even more complicated, and we have to use again iterative calculations in which the exchanger needs to be divided into different zones, and then we do a balance of energy and pressure at the same time, because as I said that here we have energy balance because the energy is being circulated between the distillation column and the heat here, and that by using that heat you are generating vapors. But at the same time, because you are using natural circulation by the density difference between the liquid and the vapor stream, and then you are using a natural head, velocity head, to generate the circulation. So you have to solve the energy balance and the pressure balance or pressure head equation at the same time. Okay, and this was done by Frank and Prickett. They performed a range of simulations, and again, this is an empirical correlation. It means that they just did experiments and tried to drive this expression, and they shown their analysis graphically by this equation here, where Q is a function of delta T. Okay, and these are all the all the constants in their equation. And if you have an aqueous solution, you can use this equation. But if you have an organic solvent, you have to use even more complicated equation here, where you have delta T is the mean temperature difference between the heat and the transfer surface and the bulk of the fluid. Then you have another term that is TR, that comes from thermodynamics. Okay, so just like critical pressure, you have critical temperature. And if you take the ratio of your arbitrary temperature or any temperature with the critical temperature, you get what we call reduced temperature. Okay, so when we are using Frank and Pickett equation for the heat flux calculation of a vertical thermosiphon reboiler, we have to be careful that this equation is accurate in the range for TR to be in the range of 0.6 to 0.8. Okay, and this equation shouldn't be used at a pressure below 0.3 bar. So we introduced several empirical relations in this lecture related with the boiling of the system, and you might see many other correlations in literature as well. So please bear in mind that none of them is correct. Okay, so when you are doing chemical engineering design, you have to be cautious regarding these correlations for boiling, especially because they are notoriously unreliable, unlike other heat transfer phenomenon. Okay, so most of these equations that we showed today, they are actually only used for preliminary basic design of reboilers. But if you want to have more reliable design, then you have to use detailed simulations. But even then, you have to be you should treat them with caution. Okay, and these are again, for example, here for vertical thermosiphon reboiler, this equation looks quite complicated, but here you are only considering natural circulation. So imagine that if you put a pump here and you cause now a forced circulation, so you even further complicate this reboiler. And it means that now you have to divide this system into different sections based on the pressure. So for example, from here to here, what would be the pressure? And then from here to here, what would be the pressure? And then from here to here, what would be the pressure? So that even further complicate the situation, and then we have no option to go for detailed simulation or softwares to do the analysis of these complicated situations. So that is more or less all for the reboilers. Now just a few words about vaporizer. So a reboiler is a type of a heat exchanger that is used specifically for the case of distillation. Okay, but if you are talking about generating vapors from a liquid stream, uh, and you are talking about a heat exchanger, you call that heat exchanger as vaporizer. Okay, so reboilers are heat exchangers that we just call them for the application of distillation. But if you are talking about in general application, you just call them vaporizers. Another distinct difference between a reboiler and a vaporizer is that for the case of vaporizer, you have a vapor liquid separation device. And like here, you can see that you have this vaporizer here where the liquid is coming to the vaporizer and then being the liquid is being converted into vapors. and then it enter into this chamber here that is known as settling drum, where some part of the liquid condenses, and then the vapor you feed it to a reactor or to whatever system you are using it for, and then the liquid again, because of its head, it again circulates into the vaporizer. Okay, so that is the only difference that distinguish between a vaporizer and the reboiler. For the case of reboiler, we actually include this settling drum. For example, for the case of kettle design, this drum is included inside the shell of the reboiler. Okay, and that's why I was saying that for the case of reboiler, you have quite a large shell because you want the vapors and the liquid to disengage from each other. Okay, so that is all for this lecture of heat exchanger design for condensers and reboilers, and I hope that from the lecture you got an idea what are different types of condensers and reboilers, and how we can use these systems in different scenarios, and some of the correlations and design equations that we can use for these systems to do a preliminary design of these heat exchangers. So that's all. Thank you so much for your time. See you in the synchronous session.